What specific problem does Q-Sparse aim to solve in the context of large language models, and why is this significant?
Q-Sparse aims to solve the problem of high computational costs and memory footprint associated with large language models, LLMs, during the inference stage. This is significant because the efficiency of LLMs is crucial for their deployment in real-world applications, where resource constraints are common. By enabling full sparsity of activations through a top K sparsification function, Q-Sparse reduces both the computation required for matrix multiplications and the input-output transfer of parameters, which is a major bottleneck in inference. The approach not only enhances efficiency, but also maintains competitive performance compared to dense models, achieving results comparable to dense baselines with a significantly lower number of activated parameters. This efficiency gain is particularly important as the demand for deploying LLMs in various applications continues to grow.
How does the proposed Q-Sparse method work? Illustrate step-by-step the main components, including the top K sparsity function, squared ReLU function, and straight-through estimator, STE.
The proposed Q-Sparse method operates through several key components to enable full sparsity of activations in large language models, LLMs. First, it employs a top K sparsity function that selects the top K activations from the input tensor during matrix multiplication, effectively masking out the less significant activations. This is achieved by creating a masked tensor that indicates the top K elements based on their absolute values, followed by an element-wise multiplication with the input tensor. Second, to enhance the sparsity of the activations further, Q-Sparse utilizes a squared ReLU function defined as ReLU x squared, which is integrated with the gated linear unit GLU in the feed-forward layers, resulting in a ReLU squared GLU function. Lastly, the method incorporates a straight-through estimator STE for backpropagation, allowing gradients to pass through the sparsity function without being zeroed out, thus mitigating the vanishing gradient problem, especially at lower layers. Together, these components enable Q-Sparse to maintain high performance while significantly reducing computational costs during inference.
What advantages or improvements does Q-Sparse offer over existing methods for sparsity in large language models, particularly in terms of efficiency during inference?
Q-Sparse offers significant advantages over existing methods for achieving sparsity in large language models, LLMs, by enabling full sparsity of activations, which enhances efficiency during inference. Unlike traditional weight sparsity methods that struggle with parallelization on GPUs and can negatively impact model accuracy, Q-Sparse utilizes a top K sparsification function that selects the most impactful activations, thereby reducing computational load without sacrificing performance. Additionally, Q-Sparse incorporates a squared ReLU function to further enhance activation sparsity, leading to a more efficient inference process. The empirical results demonstrate that models using Q-Sparse can outperform dense baselines with the same inference compute budget, achieving comparable performance while significantly reducing the number of activated parameters. Overall, Q-Sparse not only maintains high performance, but also optimizes the inference stage by minimizing the input-output transfer bottleneck associated with LLMs.
Can you describe how Q-Sparse was validated or tested in the experiments, what datasets and benchmarks were used, and how were the results evaluated?
Q-Sparse was validated through a series of experiments involving training language models with both full precision and 158-bit quantization on the Red Pajama dataset, utilizing 50 billion tokens. The performance of Q-Sparse was compared against dense baselines under the same training conditions, specifically focusing on various language tasks such as ARC Challenge, HelloSwag, Winagrande, MMLU, and Truthful QA. The results were evaluated based on observed losses and performance metrics, demonstrating that Q-Sparse with a 40% sparsity ratio could match the performance of dense models with equivalent model size and training tokens. Additionally, in the fine-tuning phase, Q-Sparse was shown to achieve superior performance with fewer activated parameters compared to the dense models, indicating its efficiency. The experiments also included an ablation study to assess the impact of the top K sparsity function and the straight-through estimator, STE, on model performance, further validating the effectiveness of Q-Sparse.
What specific results were achieved by Q-Sparse in comparison to dense baselines and other sparsification methods? Provide details on the performance metrics and findings from your experiments.
Q-Sparse demonstrated significant performance improvements compared to dense baselines and other sparsification methods in various experiments. Specifically, Q-Sparse with a 40% sparsity ratio matched the performance of dense models with the same size and training tokens, indicating its efficiency in maintaining accuracy while reducing computational costs. In the context of 1-bit LLMs, Q-Sparse outperformed dense baselines under the same inference compute budget, showcasing its compatibility and effectiveness. Additionally, when evaluated against the reluffication and DRELU sparsification methods, Q-Sparse achieved higher sparsity ratios and better performance across multiple language tasks, including ARC Challenge and MMLU. The results indicated that Q-Sparse could fine-tune dense pre-trained models into efficient sparse models with minimal accuracy loss, achieving comparable performance with fewer activated parameters.
What limitations or potential drawbacks have you identified in the Q-Sparse method, and how might these impact its applicability or effectiveness in real-world scenarios?
The Q-Sparse method, while effective in achieving full sparsity of activations in large language models, LLMs, has some limitations that could impact its real-world applicability. One potential drawback is the reliance on the straight-through estimator, STE, for backpropagation, which, although it mitigates the vanishing gradient problem, may still lead to suboptimal gradient flow in highly sparse settings. Additionally, the Q-Sparse architecture is not inherently designed for batch training and inference, which could hinder its scalability and efficiency in practical applications where batch processing is essential. Furthermore, while Q-Sparse shows promising results in terms of performance and efficiency, its integration with existing models, particularly those using different activation functions, may require additional adjustments that could complicate deployment. Lastly, the performance gains observed with Q-Sparse are contingent on achieving an optimal sparsity ratio, which may vary across different tasks and datasets, potentially limiting its generalizability.